Okay, so before we take a little practice quiz that we had promised to do today, I want to go over some things from last time. So last time we introduced the relationship between electric field and electric force. Okay, so this is really essentially the definition of electric field. It's the, if we wrote it this way, we could say E is equal to F over Q. It's the electric force per unit charge. Okay, so it's a force per unit charge in units of newtons per coulomb. And so if we can figure out how a charge particle is affected by an electric field, how the force acts on it. And then our second idea we talked about last time was the electric field due to a point charge. What causes electric field in the first place? And we have the idea that an electric field is created by charged particles. Electric field is set up basically everywhere in space. And we can run a fun little program here. Let's see if I can get this. This gives kind of a extreme example, but an idea of visualization of what this charge is doing. We have here a charged particle, and what I'm drawing, or what the program's giving, and then let me see if I can kill the light so everybody can see this. So what the program's doing is at just lots and lots of different observation locations, sort of in a cubic sort of array. I'm just picking spots that's extending back in the negative z direction and in the x and y direction. We see the directions of the electric field at these various observation locations made by this positive charge. Okay, so as I drag the positive charge around, we see that the electric field is always pointing away from the positive charge, and you can see when I get really near an observation location, that area gets really huge, okay, because of this 1 over the distance squared dependence. And so I can move it around, but everywhere in space, the electric field is pointing away from this positive charge, and of course the field is larger at observation locations closer to the charge, and it drops off with distance as you get farther and farther away. Okay, so that's just kind of a visualization of the way you can think about charges making electric field everywhere in space. Okay, and then once you have an electric field and you place a second charge in that field, you could calculate the force on that charge. Okay, and just a quick review of the directions here. We said that if you have a positive charge and you have some observation location A, and I want to find the electric field due to that positive charge. Let's call this Q, just to distinguish here. Let's call this Q1, and say Q1 is greater than 0. So the electric field, based on this equation, is going to point in what direction? Point with your fingers. At location A, the electric field due to that Q1 should be pointing that way, right? Away from positive charges, so directly away. So we can say that's E1, okay? If I were to place a second charge at that location, and I wanted to find the force on it, so let's say I place a positive charge here, call this Q2, we can now look at this other relationship and say that, okay, E1's pointing to the right, Q2 is positive. What's the direction of the force on Q2? Also to the right, right? Because I'm multiplying a positive by a vector. I get a new vector in that same direction. So that's going to be pointing that way, right? And that agrees with what we would think, right? Two positive charges should repel each other, so the force should be to the right. But if I placed a negative charge there instead, I should get a force in what direction? Other way, right? Multiply Q2 times this electric field to the right. Q2 is now negative. And I get a force that is pointing in the opposite direction of the electric field, okay? And you could do this, just to work it out real quick, you could do this if you had a negative point charge creating an electric field. If Q1 were, draw a different situation, Q1 were less than 0, and I have then at location A, electric fields due to negative charges should point that way, towards the negative charge, right? So that's E1. And then I could do the same thing. Okay, we call this, just to distinguish, we call this the source charge. And if I'm placing a second charge there, call it Q2. If I place the positive here, this is my source in this case. Place a positive here, then the force should be in what direction on that second charge? Same direction as the electric field, okay? And that kind of makes sense because if we have a negative charge and a positive charge, they should, two unlike charges will attract, right? So the force should be that way. So we get what we expect. Same thing if I had placed a negative charge here. A negative times E1 gives me a force in what direction? That way, opposite direction, okay? And so two negative charges should repel, right? So that the force makes sense, okay? Do we get the idea? See how this is making sense? Yes. Well, I'm basing it off of here, right? Because this comes back to we're defining we are determining that the electric field due to a point charge is from this relationship, this formula, okay? And so think about how we determine this. If we have an R vector, okay, so what is this R hat? This R hat is a unit vector that points from the source to the observation location by definition, okay? So I define an R vector that points from the negative charge to the observation location, call that R, and then R hat is just a unit vector in that same direction, okay? What's multiplying R hat? Well, we have 1 over 4 pi epsilon 0, that's a positive constant. We have R squared here, which is a magnitude, so that's positive. But the Q1 in this case is less than 0, right? So if I multiply a negative by R hat, I'm going to get an electric field vector that points in the opposite direction of R hat, okay? And so what we just went through is we showed that the electric field has to point away from positive charges towards negative charges. It has to be that way because when we place a second charge there, we get back the force that we would expect, right? We'd expect two positives to repel, two negatives to repel, a positive and negative to attract, and that's in fact what we got, okay? Other questions here? These two relationships are so important that you probably should just, in fact, you really definitely should just memorize them. These are essentially the two fundamental ideas behind electric field, or fundamental principles, if you want to call them that, although not quite fundamental, but fundamental enough for our purposes. We're going to be using these to build up a lot of stuff, and we're going to be coming back to these over and over again throughout the semester. So they're so central, they're so fundamental that we should just commit them to memory. And then you just know them, and just sort of know them inside and out. Okay? Questions?